Hello, this is on Galois correspondence. Which aligns two different structures. First I will start with setting things up. I will start with a Galois extension of fields. And the alignment will be between two what are called lattices. So on one side we have lattice of intermediate subfields. Well, what we have is a certain picture, so we have the field F above, the field K below everything, so everything in between, all fields which contain K and are contained in F are to be listed in this lattice. And for current purposes there will be just this collection of all subfields in F which contain K. So that is one side of the Galois correspondence. The other side is the lattice of subgroups of the symmetry group of the extension of the automorphism group of F fixing K. And we have to flip it upside down, so the reversed version of this lattice will be sitting on the other side. And flipped upside down, at the top it will have the trivial subgroup, the identity subgroup, and the whole group will be at the bottom, and everything in between, so subgroups in this group, will be somewhere in the bulk of this lattice. So the statement of the Galois correspondence is that these two structures are isomorphic, are identical. The identifications are very explicit. Going from subfields to subgroups, we have the following construction. For any subfield of F, we just look at the symmetry group fixing this subfield, so we look at automorphisms which are identical on E. Going the other way around, if we have a subgroup, we can construct a subfield of F, so the subgroup is some collection of symmetries of F. We will construct this subfield as a field of invariance. So we look at all elements in F which are fixed by all elements in the subgroup. And that's easy to see, it's very straightforward to see that this is a subfield closed under all arithmetic operations. So what I'm going to do now is to argue that these two maps are undoing each other, that they are mutual isomorphisms. The key facts which I'm going to use, just two key facts, which can be neatly summarized as follows. So in this lattice I have something else, not just the picture, but some numerical information. With every h I can associate a number, a natural number, which, say, for this h between f and d will be the degree of f over e, the dimension of f over e. On the other side, I also have this labeling on edges. So for this h it will be just the order of g, and in any way in the bulk, so for this h it will be the index of g inside the full automorphism groups. So the facts are really saying this, that these correspondences we have, they preserve these measures, these numbers. So the first fact is saying that if we look at the index in F of some subfield, it will be the same as to transport it along this map to the other side of the correspondence. So to have this subgroup and measure its size. And of course this is true since since F as an extension of E is also Galois. So that is the fact that this map preserves the numerical numbers attached to the edges. The other fact is that this map also preserves it. So that would be saying that the index of the subfield of invariance, the degree of this extension is just the order of the group. And that is verified somewhere else. So these are the two key facts which will now allow me to prove that these two maps are undoing each other. So first, let me go this way and then return. So I'm starting with the field E, and if I'm moving from the lattice of subfields to the lattice of subgroups, I'll have to contain this symmetry group over E, and then if I'm going back, I'll have to use it to compute the subfields of invariance with respect to this subgroup. By the definition, the elements in the subgroup, they fix pointwise elements of the subfield E. So the field of invariance will definitely contain the subfield E. But it's actually not just a subfield, so the containment is obvious from the construction. But I'm arguing that they are actually the same. So let's see really what happens. We have F, we have this subfield of invariance, and we have E sitting inside. F extending anything is a Galois extension, so the degree of this extension is equal to the so the degree of this extension I would rather compute using this fact, and the degree of this extension is the size of the group. But yeah, slightly reversing logic, but this is a Galois extension, and its degree it's also the same as the size of the group by the Galois property. So this degree is equal to the whole degree, and that means that these two have no difference in between, so they are the same. Okay, now starting from subgroups, going to subfields and returning to subgroups. So this procedure, say I'm starting with G, but doing this loop, I'll have to compute the subfield of invariance, and then I'll have to look at the symmetry group fixing the subfield. And again, obviously G sits inside by the construction, so any element of G will be fixing the subfield of invariance of G, and so it will be inside this whole group. But again, I'm arguing that this should be the same, and the argument is the following. So let's first observe that again this extension of F extending something in the bulk is Galois, and so the degree is equal to the automorphism group, but also the degree is equal to the order of the group G, and so the G in the automorphism group will have to be the same. So that's it. Let me write it down. So G is equal to the degree by this fact, but also this degree is equal to the order of the automorphism group by the Galois property, and so these are the same sizes and they have to be the same as groups. And that is it. We will use this correspondence. Really, it practically works from right to left, so knowing subgroups is way easier than to see all subfields, and that information is translated into subfields along this map and give us the insight into inner workings of algebraic numbers. And yeah, that is to follow. See you soon.